Well, hello there, and welcome back for more Advent of Code. So, where were we? I think we were on the last stretch of Advent of Code 2023 on 2024 already, but who cares? And yeah, it's only 3 puzzles more to go, and it seems like, oh, look at that, day 25, the last one is kind of sandwiched between 23 and 24. That's cool. But it seems like we are on the last island. This was the snow producing thing, and we have the water flowing from the island above. So that's nice. Day 23, a long walk. And it seems like it's another grid puzzle. Yeah, this Advent of Code has been really chock full of grid puzzles, which is nice. I won't complain about that. The elves resume water filtering operations. Clean water starts flowing over the edge of islands. And my cat wants to get into my lap. It's important to let her do that. She's over here. But yeah, oh man, it's a bit warm, especially with my cat on top. Well, I may turn on the fan or the AC in a bit. But yeah, clean water starts flowing over the edge of island. They offer to help you go over the edge of island too. Oh, nice. So they are throwing me away with water? Just hold on tight to one end of this impossibly long rope and they'll lower you down a safe distance from the massive waterfall you just created. Okay, so we are going down via an impossibly long rope. As you finally reach Snow Island, you see that the water isn't really reaching the ground. It's being absorbed by the air itself. It looks like you'll finally have a little downtime while the moisture builds up to snow-producing levels. Snow Island is pretty scenic, even without any snow. Why not take a walk? Okay, so the water is not getting to the ground. I wonder if this is actually something that would happen if you have like a giant supermassive waterfall. Like would the water like disperse on the air and like form clouds or humidity? I don't know, because like on very long waterfalls you get this mist that is seems to be like reminiscent of this thing. This would be like much higher, so maybe this is although it sounds like fantastical, maybe it's actually grounded on reality. I don't know. But okay, why not take a walk? There's a map of nearby hiking trails, your puzzle input, that indicates paths, forest, hash, and steep slopes. So like arrow symbols. Yeah, I'm surprised like how many puzzles have been using the dot and hash symbols on all of these Advent of Code puzzles. Like, I don't know, maybe like half of them probably. But okay, it seems like this is kind of a maze with some steep slopes in some of the paths, I guess. You're currently on the single path tile in the top row. In the single path tile. Okay, so you start here and I guess you get down here. Your goal is to reach the single path tile in the bottom row. Because of all the mist from the waterfall, the slopes are probably quite icy. If you step onto a slope tile, your next step must be downhill in the direction that the arrow is pointing. To make sure you have the most scenic hike possible, never step onto the same tile twice. What is the longest hike you can take? Longest hike? This is an interesting like twist on finding shortest paths. In the example above, the longest hike you can take is marked with O. And you start and starting position is marked S. So yeah, you start here and you do lots of walking. It seems it's a bit difficult to follow, but all right, it's good enough. Here there's an interesting thing. There is a slope over here, but you cannot cross it because, yeah, slopes are like one-way doors, kind of, or one-way walls. You can cross them in one direction, but not in the other, which is interesting. This hike contains 94 steps. The other possible hikes you could have taken were 90, 86, 82, 82, and 74 steps long. Find the longest hike you can take through the hiking trails listed on your map. How many steps long is the longest hike? And the input, I guess, would be just a larger map. It starts also on the top left and it ends on the bottom right. That's kind of pretty also. Okay, so longest path. How do we go about this? Is there some like longest path algorithm? Longest path algorithm. Longest path problem. Okay, didn't know that this was. Look at that. Path is called simple if it does not have any repeated vertices. The length of a path must either be measured by the number of edges. Okay. Oh, it's an NP-hard problem. Wow. Okay. Interesting. This means that the decision problem cannot be solved polynomial time for arbitrary graphs unless P equals NP. So I'm sure that the element of code problem won't have us rely on P equal NP or trying to prove it. That would be awesome, you know, like an impossible advent of code challenge, and maybe someone gets to finally prove P equals NP or P not equal NP. But okay, this is interesting. Give me a solution. I wonder if the pathfinding crate that we are using, Rust pathfinding, this is the crate that we have been using for Dijkstra algorithm and things like that. Does it have a longest? Oh, look at that. Longer and longer paths in a weighted graph at the cost of multiple similar examinations. Iterative deepening A star. Longer and longer paths. Interesting. I didn't know that this was a... Well, it's actually kind of a similar problem, kind of like the traveling salesman problem, where you want to visit like all the nodes. In this case, it's like, okay, maximize the amount of nodes that you can visit. Look at that. There is also some dead ends in here. Oh, this is all like a dead. Oh no, this is not a dead end because you can go down here. Oh, I wasn't seeing this correctly. But one interesting thing about this, like the shape of this, is that there weren't that many paths that could be taken. Only a few. So that's interesting. Like it sounds like, even though this is like NP hard or whatever, like the amount of combinations is not too high, so we can probably find all the paths and then take the maximum. So maybe some of these pathfinding algorithms that's ID star, no, these things, compute the shortest path. No, why does it say the shortest? Oh, this has links to Wikipedia now. I thought that this thing had links to IDD. There's something that I'm not understanding here. IDA star. Is this thing? Yeah. But it doesn't talk about longer and longer paths in a weighted graph at the cost of multiple similar examinations. It's total cost. So okay, like A star, it has a heuristic twice in the path. Okay. It's also like sort of a complete Dijkstra or something like that. No, it's not like Dijkstra, because Dijkstra won't find longer things than necessary. But it's sort of if we were doing like a fluid field, not fluid, but a breadth first search or a deep depth first search would also give us the different paths, I think. Like I think we could also try to, like, instead of using a crate for this, try to actually think about how to solve it. But I'm getting a bit warm with my cat on top, so I will cut the recording for a bit. What was the shortcut for this? I think it's this. And I'm back now with the ceiling fan turned on and with my cat still on my lap. So we were checking these algorithms. The ADI star, I don't understand what's the shortest path you think using. Iterative deepening A star. So it's like a variant of A star, but still is the shortest path algorithm. What is the shortest path? Yeah. So I don't think that these guys will help. Unless we do, what would be some way of doing this using, like maybe using some of these algorithms? I'm not sure. I can think of a few, I think. So, like if I want to reuse some of these shortest path algorithms, one thing that we could do is, okay, in these algorithms what we have is a function that will, like you give it a function that will give you the successors, like, or the connected nodes on a graph. So if we start here, like, also the successors of this seems to be very, very restricted until you get to some like connection where you can take, it's not connection, the bifurcation. When you get to a bifurcation and you can take two paths instead of going on, because if you're going along this trail, like you're here and then you go here, you can only keep going to the right. Like you cannot go back because you cannot go like repeat a tile. So most of the tiles only have like one possibility to go. So even though this seems like a big graph, we could reduce this graph to like this would be a node, the starting node you want to get there, but all of these intermediate things we could not consider them nodes and just keep advancing. That's actually something that I never that I never thought of on this kind of problems. And I don't know if this is the first like maze that we have. We also had like a pipe maze on another puzzle, but this is the first time that I'm thinking this, that when you want to get like the successors, if you're here, instead of saying, hey, yeah, this is the successor, you can just walk until you find a bifurcation and you say, okay, this is the successor. And this successor has a couple of possibilities, and you walk along those possibilities and until you find like here, for example, or if you go down, you walk until you're here. So you reduce the graph cardinality by a lot by doing that. That's interesting. I never thought about that. Maybe here we can do something similar to that. And this is kind of like a directed sort of graph also, because for example here you can go in both of these directions, but sometimes you're going to find, I don't know where, but sometimes you're going to find, I guess, some roadblocks by these slopes that you cannot go. Like here, for example, if you go down here, this is an interesting one. Here's a four-way intersection, but if you come here from the top, you can go down or right, but you cannot go left because of the slope. And that's interesting. And similarly, if you come from the left, you cannot go right or down. So it's like the map is almost encouraging you to go in the right direction and not have loops. That's interesting. I don't know if you can have loops in here. If you can't, then this might be a simpler thing to solve. Can we maybe check if we have loops? Let's try to, let's for example consider this point, which is quite interesting. If you go to the right, you can go here, then down. You cannot go up. So since you cannot go up here, it's like you cannot connect and you cannot pass through here either. So you cannot come back up again. Yeah, you can only go. Yeah, that's interesting. It's very directed. And also on the down way too. I don't know if the actual input has this property, but the sample input seems to make it impossible to repeat some of the tiles. Interesting. That's interesting. So one way that I'm thinking of this problem, like reusing the shortest path algorithms, but I don't think that's a good idea to reuse this pathfinding. Shortest path. Wait, I was looking for longer, but maybe it says short. Long seems to be the antonym or the contrary word, but find the cycle in an infinite sequence. Maximum flow in a weighted graph. What is the maximum flow? Shrunk. Find k shortest path. What are also k shortests? I don't know what the flow of a graph is. I don't think that this is related to what I'm looking for. So I'm kind of pathfinding my way between tabs and trying to reuse some existing traits. Directed graphs, undirected graphs. Find the maximum match. What? Maximum matching in a weighting bipartite graph. Okay. Yen's search algorithm. Oh, look at that. You can find... this is interesting. Maybe we can use this. You can find the k shortest paths. Huh. Wait, I want to see the... I didn't want to see the Wikipedia article. I want to see... Let's close things that are not promising. I want to see the docs for this. Yen, k, haha. We have a k. K shortest path using... The return and path include both the start and the end node and are ordered by their cost, starting with the lowest cost. If there exist less paths than requested only the existing ones, if any, are returned. Yeah, this seems like... I don't know why it's a k problem, like with... I have an idea of why it might be like a problem with a given size, because like if we try to think of all the ways that we could do is, although I think I had the suspicion that this thing is very directed and that we won't really need to check for loops, but this is just a suspicion, and maybe the sample doesn't have that. But maybe the real input does have loops, so we have to be probably wary about that. But we could check that also, like trying to do some sort of fluid field or something like that. But I was thinking that why does this algorithm, this Yen's algorithm, it finds the k minus 1 deviations from the best path. Like, okay. I wonder why it needs this this k, and I'm thinking of like if you think about like following a trail. Here, when you have a bifurcation, it's like you can continue with the original trail, and then you know when you are back to it. But then, if you don't reach the end with that, or if you reach it, but then you have to compute the other, it's like the other one also has to, it's like starting a new path, but you also want to know where have you been. So you could have like two different integers or some numbers to identify each path. And maybe that's, I'm not sure though of what I'm saying. Because there's always like good and bad ways of implementing this kind of searching algorithms, and bad ways would be wasting a lot of memory and copying lots of things, and better ways are trying to minimize that memory. But I am tempted to maybe try to use this Jens algorithm from the pathfinding module, throwing in a pretty large k, and try to get an answer for part 1, and then see what part 2 is about. Which, before, I would like to also maybe think about a solution for this, like thinking it on my own instead of using an existing algorithm. But just in case that part 2 is super complicated, I think I just want to first get the solution for part 1. So let's jump into the code. Finally, code. Enough talking already, right? Let's do the usual copying of the templates and the usual indexing of the text editor that takes a while. This was a long walk or something like that. Don't remember the name. A long walk. Okay, almost. A long walk. Walk the line. And we also copy the input directory. So let's close everything else. No, not the templates. This thing. The actual input is gonna be the giant maze. We can close it afterwards. Look at that beauty. Then the sample output was something like 94. Whoop, 94. And the sample input is this thing. No, not everything, just this. Okay. So the first step, as usual, is going to be to parse this grid, for which I think I should already have, like just as we have like a read string utility function or our parse numbers. I think it would be nice to have like a parse grid function, just to check, that the grids are square or rectangular, things like that. I don't think we need to check anything for this. Have our starting node and things like that. It's important to not go back. But yeah, these algorithms are going to take care of not going back to things or anything. So let's just parse the grid. Let's grid be, we're gonna do our usual input lines, bump the font size, close the sidebar. We're gonna map each line. Do we need to have the slopes and those things? Like, do I want to model the tiles? I don't think so. Let's just have a 2D vector of character. So we're gonna have characters, collect, we can use collect vec for this, and then collect vec again. And with that, we don't need to declare types. This is a vector of characters. That's great. What else do we want? With that, we should have the grid. Then let's just try to call this yen function. So we're gonna use this guy, and we have a start. This is kind of the same signature as Dijkstra, where you have the start is successors function and success function, and the k, which is just going to throw a big number and see what happens, basically. Yeah, let's use this guy. And let's call yen. No, yes, yen. The nodes. What are the nodes going to be? I think it should be good enough to say like just the x and y positions. I'll look at that. If we highlight, we can see these paths a bit better. This also seems like a nice puzzle to draw things on the terminal, but let's just try to get to the answer. So yeah, let's say that let start is gonna be the xy position. So the x is gonna be 1 and y 0. And we're just gonna pass the starts. I think this wants a reference to these guys. So let's just have a reference. And actually, you know what's in successors and success. Let's inline this because I think Rust makes a better job of type inference when you inline things. So then comes the successors function, which is the interesting bits. We're gonna get an xy, and this should give us the successors. So we're gonna access the grid at this xy and say, okay, grids y and x. We want to, do we want to see where we are standing? Maybe. Maybe, right? What does it say about the slopes? Like, when you go into a slope, you can only walk in the direction of that slope. So I don't know if I should check, like here, check what's the direction of the slope, or try to walk on top of it and then just check my current position and like slope down from there. If you step onto a slope tile, your next step must be downhill. Okay, must be downhill. So that's interesting. If we are here and we move here, the next step must be downhill. So we are going to try to come here. So this will be the neighbor, and it will be repeating a neighbor. So the algorithm is just going to discard this thing. So I'm not going to try to reduce the graph and try to do that thing of that I mentioned of like if I'm here, say that the neighbor is this node because it's the next like bifurcation. I'm just going to say, okay, the neighbor is this, then it's this, then so on. Like try to walk one by one and hope that the algorithm is intelligent enough. So we're going to access the grid here and say let tile be this. I'm probably going to need some type annotations here. Yeah, let's just put some in here so it knows what they are. don't you already know with this? Oh, you're receiving a reference, that's the reference here, and that's fine. So that's one thing that it needs, the successor function. We will think about that later, but it also needs the success function, which should be quite simple. We're gonna receive also an xy node, which we can dereference, and we're just going to ask if x is, let's take the dimensions of the grid, let's height be grid length, and let's width be grid 0 length. And also this would be a nice thing to have in a parse grid function, that, you know, to check that all the lines are the same width, so you kind of know that it's an actual grid, and maybe that it's not empty, because otherwise this thing would complain. But let's not think about edge cases like that now. So we want to have the x being at, like, basically width -2. So if this is this, and y is height -1, right? And also we are counting 94 steps, so we are not counting the first one. Well, it's gonna be enough by one error in any case. And then we need to pass a k. So what do we pass here? How do I see the... Okay, the documentation for this. This is the k thing. I'm just gonna pass 100 and see what happens. Like, it should work for the sample, but I don't know if it will work for the input. But we will see. And this thing, yeah, it's complaining about the successors function, but that's nice. And we should have then a vector. Okay. And then for this vector, each vector has a vector of nodes. Cool. And the cost, the total cost of that. And I think it's starting from the includes both the start and the end node, and are ordered by their cost, starting with the lowest cost. Okay, so we want the last one. Okay, so let's just have, let's k shortest, k shortest paths, and, you know, let's also be good citizens and extract this into k. Let k be 100. And then we're going to print line. What do we want to know? Let's just have the k shortest paths. Into iterator, like, consume this thing and say, okay, map it, and again collect vec. We're just going to map it into their costs, right? That's what we want. So we're gonna receive a tuple, which is a path and a cost, and we just want the cost. Okay. And finally, the successors function, which is the interesting bit. So what are we going to do? I think we can basically match on the tile and say, well, basically ask about these different special characters. Like if we are standing here, we wanted the only direction to be up, basically. But do I want to do that? Well, yes, that I want to do that, but I'm also going to want to filter out like invalid. Well, this thing actually, this shouldn't go. That's interesting. Like we shouldn't care about out of bounds conditions because we are always starting from here. That's also sorry, because we are always having like a wall at the ends. So out of bounds conditions are not really interesting. Yeah. What I mean is, sorry, I'm sort of thinking something and trying to speak at the same time, and that seems to be a bit too much for me. What I meant to say about out of bounds condition is like we are always going to hit a wall when we like we cannot go out of bounds of the grid, so that's nice. And if we are here, we are already at the end, so it won't compute the neighbor successors nodes for this one, so it shouldn't be a problem. So what do we want to say here? One possibility is to like make this function return, for example, a vector. And you know, if it's up, we just say, okay, return a vector with a single app neighbor. Let's actually do that and not worry about anything. So like performance would be the you know, extra allocations is kind of a problem here. Doing this is kind of super unnecessary. We could start with the 4 directions and then filter out what we like the invalid directions. But let's not worry about that now. So if we are on this tile, we can only move up, and that will mean saying, okay, same x, but y -1. Sure. If we are, well, let's say the same thing, but down, it's going to be y +1. Then we have a similar thing for left. It's going to be y -1, and sorry, x -1 and same y, and to the right is going to be this. Then if we are on a wall, then we have no neighbors basically, so it's going to be an empty vector. And if we are on a path like anything else, we're gonna have our 4 usual neighbors. So that's kind of also the repetition here, which is not super nice, but these are basically all the neighboring tiles. We can, yeah, look at that. Multi-cursor to the rescue. So, okay. Would this work? And let's say if anything else, let's just say unreachable for now. We can refactor this later. And what do you complain about? Oh, you also want the cost, right? Yeah. Okay. So you have this. The cost will be 1 for any of these. So let's say, let's neighbors be this. Beautiful. Right, and then we're gonna say, okay, neighbors. This is quite horrible, but whatever. Position, and we're gonna say position and cost of 1. And this is an iterator that consumes this thing. Good luck optimizing this, but it's not complaining, so let's actually run this and see what we get. Cargo run. This would be day 23, a long walk, and the input is gonna be a sample. So what do we expect to have? We expect to print the cost of these things, so we should see these numbers, or maybe one more than these numbers, but something similar to this, hopefully. I have little hope of that, but let's try. No, we got a panic. Subtract with overflow. Okay, so we are going out of bounds. That is fantastic. So, okay, yeah, we're gonna start out of bounds already, which is a pity, because we start at y0, and we are going to be computing this, which is bad. We could use signed integers for this, and then like filter out the things that are in bounds. Ugly. I mean, yeah, could be one possibility, I guess. Yeah, let's have. What do I want to have? Yeah, if the tile is out of bounds, I want to say nothing, bro. Just nothing. Just nothing. Yeah. So how do we make this the best way possible? Do I bite the bullets and try to, like, because I want, after all, I will want to refactor this into something good. Into something good. Yeah. Okay. Yeah, let's actually bite the bullet now and just have our usual let directions. We're gonna just have the difference of all directions. So let's start with left and right, up and down. I don't know why I would want to go left or up before down or right, which are the things that's generally the direction I'm interested in. So let's for once put the right before the left. Kind of what my country is doing now. Okay. So I want to have these directions and just say what? We're gonna intuiter them. So we're gonna already get rid of these allocations for vectors. So let's do things right. Sometimes doing things right is faster and better than doing things wrong. So we're gonna filter out the invalid directions and then just do this kind of map. Just put a cost of 1 into each of them. And I think that should be it. And we are gonna do the matching of the tile inside of this filter. Okay, so here we're going to get neighbor x and neighbor y. No, actually this is the direction, so dx, dy. Yeah. Let's put the match inside of here. And we are gonna, what are we gonna do? Yeah, we are gonna filter out, right? I think so. So yeah, let's do let neighbor x, neighbor y. So now that we have the directions, these are signed integers, we can do our x and y, which are unsigned. So x wrapping add signed, and we add dx, and then y wrapping add signed and add dy. Great, so now we have wrapped around if it's wrong, and if we always want this to be like, if we want to be good citizens, we could say do the checking here, right? I guess so. We would have the neighbor. So do we count the neighbors? Like, this is also an interesting thing, is do we count the neighbors that do we do the checks of the walls on the neighbor itself or on the tile itself? Like, we consider the wall and then we say the wall has no neighbors. I think that it will be easier to yeah, I think it would be easier to just consider the neighbor and see if we can move there or not. Yeah, right, we don't need the actual tile. We assume that our current tile is, I think that sounds a bit better. So yeah, we want to do this. And actually, do we need the map? Well, we will see. But here we are filtering the, oh no, we don't need, here we are filtering the directions. I don't want to filter the directions. I want to do sort of a filter map actually here. And then if this goes right, if this is a valid neighbor, I'm going to return nx and ny, And we can already do the cost of this, which will be 1. So we don't need the mapping here. Okay, we're gonna do something like that. And we are also the xdy, what do you complain about? Closure may outlive blah 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 blah. Yeah, move. That can be written more simply as a map. Yeah, sure, but let me filter some things. So we need the neighbor tile. So let's say let tile be something like this, but we are actually going to bounce check here. That's what I wanted to do, the wrapping thing. So let's get the y and let's get, this is an optional, so let's then get x, and this is also an optional, and now it shouldn't complain about all the thing. And now it's trying to get grid. Well, let's have the grid be a reference, right? Yeah, that will make you happy. Yes, this tile can be forgotten. And now we have the neighboring tile. Oh, look at that, already have a bug here. This shouldn't be x and y, this should be ny and nx, the neighbor tile. And so, if the neighbor tile is up, we can only, can we get to, this is kind of a edge case that I wasn't thinking about. In one of these bifurcations, I don't know if we can get to like something like this, to a slope. I don't know if we can get to a slope from a position that is not, like if we can get to an up slope from the left or from the right. But yeah, okay, we can assume this maybe. So we want to filter this, do a filter map. So we're considering, can we go into here? What we were doing before, which now I don't know if was a better logic or not, was consider our actual tile and say, okay, my neighbors are this. But now we are considering the neighbor tile. And here we basically want to say, okay, if my neighbor tile is up, then I should only go there if my direction is up. So basically dx, dy, right? That's kind of what we want to do, I think. Match tile, if, say, if my direction is up, is asking basically if the dy is -1. In this case, we are going to say now in this case this is valid, but if we are getting here, well, basically we can ask the other way around. If our direction is down, dy is down, then we shouldn't get into here. So we're gonna say none in this case. Yeah, that's kind of what I want. So this is basically the contrary. Hello. I got visited by my cat. She's so cute. All right, cute moments of the day. So if we face a downward slope and we are going up, then we are also going to say nope. And we're gonna do basically this thing for this other two, I think. if we find these and we are going right, we don't go there. And if we find this and we were going left, we don't go there. And if we find the wall, we don't go there in any case. And if we find this, we go there. So basically we don't need to say anything here because we have filtering. And let's basically say in any other case. And my cute cat got into the desk and she immediately tried to bite my cell phone, which is not that cute. Okay, so these are the early termination conditions, the filtering conditions of this filter map. So I think this is kind of what I want. Let's run. And look at that. we got k shortest paths. And that's really nice. We got 94, and I don't know why it's 94 instead of 95, but I'm happy about that. Let's also print line. Print line found paths, and the is going to be k shortest path and length. So if we find 100 in the input, we know that we haven't explored them all, but let's actually run with the inputs. And it's taking some time. This might not be very efficient, and it seems like it's not. But it's not getting out of bounds or anything, so let's kill it and run it in release mode. What did I do? No, the binary is not called R. R is release mode. Optimized. Ooh, look at that. But it found 100 paths. So look at that. All the paths are getting longer. But still, we didn't get our answer. So let's bump this to thousands and run it with this. So are there more than 1,000 possible paths? This algorithm is not being very efficient, but also my solution is not very optimal either, because I'm considering so many nodes on this graph that could be simplified by a lot, but that's fine. Okay, now it found 252 paths, and so the largest one, I cannot see because of my face, but the largest one is 1950, the year when I don't know what happened in 1950, but is this the correct answer? No, that's not the right answer. Your answer is too low. Oof, if you're stuck, make sure you're using the full input data. What a bummer. So that was too low. That is the highest that we got. Okay. We didn't explode, but we also didn't get the correct answer. Did I make a stupid mistake on... Okay, let's go with sample. Are these things correct? 94, 90, 86, 82, 90, 86, 82, 82, and 74. So, okay, it seems like the sample doesn't have some trickery that the actual input does. So we wanted to find 1,000 k shortest paths. We found 252, so less than 1,000. but the longest of them was not as long as we wanted. It was still too short. 1950. So 1950 is too short. Let's just try something to see where is the range. I don't want to do a binary search, but that's not the right answer. That is too high. Okay, so it's less than 2050. Interesting. So we are close, but not quite. What could have gone wrong? The input looks the same. This is 23 inputs. We need to make the font size smaller to see, but also the output, the end node is on the bottom right, so that should be fine. I don't want to start like printing things because this is a giant maze. But what could have gone wrong here? So I'm thinking of some possibility, like, oh, okay, one possibility that I think I was a bit lenient when I wrote it. So yeah, right, this should give the same answer, and I don't know if I copied. So this was too long, this is too short, right? Yeah, this is too low. So here, when we go to the neighbor, we are filtering, like, we're saying, okay, if we find this neighbor, we cannot go here if we are coming down. But that's not actually the correct condition, I think. What I think we should say, because maybe we can go into an upwards tile if we're coming from left or from the right, and I don't know if that happens on the input. Maybe we can check with a text search. So this would be dot and then up, for example, or up and dot. That's also not happens, but let's say down, for example, down and dot, or dot and down. No, these things don't seem to happen. It's always with walls to their sides. So we have 60 sandwiches like this, and 60 down slopes. And for the up slopes, why no results? Hey, what? Why no results of the up slope? What is the symbol for the up slope? Did I confuse? That doesn't make sense, right? This is the caret, or yeah, I don't know how it's called, but this doesn't exist on the input. What? It is on the sample, right? No, what? There is no upwards slope. That's weird. So we never go up with a slope. We go, oh, wait, the sample, I didn't notice this. So the input, the sample and the input don't have any upward or left slopes. Interesting. Very interesting. And I wonder if there is a case. So basically this and this is something that doesn't happen because we never find this. That's good to know. That's good to know. So what do we want to say basically? We want to say don't get into here. Yeah, if we are going up, that is what we want to say, right? Yeah. Because if we get into here going up, then we would need to go down, and that would be wrong. Like we would visit the same tile again. So what am I doing wrong here? If we are going to the left, an X and Y and X. Okay, this is the tile. We are checking for this, and we know that the answer is quite close. Like it's between 1950 and 2500. So is it? This is very, very cheesy to do, but is it around 2000? Like, I don't want to do this. That's not the right answer. It's not telling me now. That's not the right answer. It doesn't say if it's too low. Because you have guessed incorrectly 4 times on this puzzle, please wait 5 minutes before trying again. Oh, okay. Yeah, I was getting a little bit cheeky with that. Yeah. I was tempted to go into the binary search mode, but okay. We know it is between 1950 and 2500. But why? Why are we not getting the correct answer here? It should be. I don't know if this algorithm is what I want to use. So what do you do, Jens algorithm? Description. What is a spur node? Spur, like spurious, I guess it's something like not necessary. So spur meaning incentive. Okay. maybe like a spike. I think this algorithm is doing something kind of similar to spur path to the sink. Yeah, it's like if you know what the shortest path is taking, it's like whenever you have a bifurcation, you want to take you want to take like the other path that you didn't take for the shortest path, and it's kind of a recursive thing or an iterative algorithm that you do that for any like bifurcation. Start the edges. Okay, you know what? I don't really know why, like, what would be another source of confusion for this thing? Like, we are not doing anything very weird here. Here we are returning none in these cases. So could we say I want to see, and we know that there are no carets, so there's not this nor left, which makes me think that I don't know if part 2 will have some of those or something, but like if the tile is right or the tile is down, I want to see which direction we are coming. Found tile going in direction dx, well, in direction, let's say dx and dy. I don't know why I'm using the font so low. Your problem here is that this is reference. Sure, like dereference this, no problem. So this is the input, this is the sample. Do we? Yeah, right, we always So I don't know why I wanted to print this, because this is just noise. It should always correspond that when finding the right we should be going right at this point because we have filtered the other case. But let's say if we find right and the x is different to 1, so we are not going in the right direction, or if the tile, and I know that the precedence of this is already right without the parentheses, but whatever. If we find down and the direction of y is not down, then we print this. So we shouldn't see anything for the sample. Will we see anything for the input? Something that we are filtering, or will we be filtering? I think we are filtering right if the x is equal to -1. So if we are going left, we filter, but if we are going up or down and we find this, we're not filtering. And does that happen? But if that happens, then that shouldn't be a problem, right? Or is it? Maybe it is. I don't know. But it takes a lot of time running for the input without the release mode. But we didn't see anything printed, so I think this doesn't happen. What a weird thing to have answers, but for the answers to be wrong like this. It's interesting. It also takes a long while to compute. Yeah, we didn't see any of the printing, so I think this is a condition that doesn't happen. We never find the down when not going down. So what's the problem then? We should then this algorithm shouldn't be wrong. We are starting from the right place and we are checking, I think, the right thing. Getting xy here, we are only using xy for adding the direction. Getting the neighbor tile, we are checking, basically bounce checking here, and we don't go into walls, that's fine. We don't go into slopes when the direction is not correct, that's also fine. So what is going on? If I print, I could print the longest path and see how it looks. Or I could try to think of my own implementation of this and not use Jens' algorithm, because it's also super slow. And I think I should be able to do some solution for this. Find all the bifurcations kind of that we find, and then sort of try all the combinations of those bifurcations. I'm not sure how to do that, but like if we are doing like sort of breadth first search of walking around, like let's take a look at the sample. Like at the beginning we don't have any decision, so we can do this on a simple loop. Then we get to a bifurcation. It's like, okay, we continue going in one of the directions, but we also take note of this node and say, okay, take the right direction the next time. Like we would have a state with that, and then we go on there. And I think we won't find also this thing again if we keep going, because yeah, we're simply like not considering that. So if we find then the end, it's like, okay, we made one path, but then we have to like pop the different alternatives that we didn't take and also take them and see where they lead us. So okay, the sample gives us 6 paths. So does that correspond with the amount of bifurcations that we have? So here we have 1 bifurcation, so we have 2 paths, presumably. Then we keep going. I would like to annotate this with something. Let's put a big X here. So yeah, and we can like find X's and have them highlighted. So we keep going here. Here we have another bifurcation, so let's also put an X in here. If we keep going this direction, we go like this. This is not a bifurcation because we cannot get into here, so we keep going. We keep going, and we keep going. This is also not a bifurcation, so okay, this X, all of this path is just doesn't have bifurcation. So that is, we took the right there. Then we took down. We go here, around here. Here we do have a bifurcation of 2 actually, because the left is not possible. The cat is moving my notebook, and she doesn't fit there because she's too fat. So here we have another bifurcation, and this is like a double bifurcation because we can come from the top and from the left. We came from the top, so if we go right, this goes this way, and we get into the same direction as before. So that's one possibility. Then we go down. Here we have a bifurcation that is not really a bifurcation. We keep going and we go out. Okay, so that was all the possibilities of going down here. If we here, instead of going to the right, we can go down. We come here. Here we have another bifurcation, which we can take to the right, and we come to the same place here, or we can go down and make this long turn over here. And this looks like a bifurcation, but it's not, because whenever we come here, we keep going in the same direction. So okay, we have like 4 actual bifurcations, very few. And why did we get 6 different paths? Because the first one, we had 1 and 2, and that's then bifurcated in 2, like, how do we count this? So the first one bifurcates in 2, so this one then goes all the way here, and this one, I think, oh, this also bifurcates in 2, so that would be 1 going all the way down, then 2, then 3, I think. That was all the possibilities of going down, and then going right goes like this, and you have 1 long one, so 4, then 1 going like this, and yeah, 5 and 6, I think. So it's not that much, but you can get to the same. We got here like from 2 different paths with 2 different costs, and one was the longest. So, but what do I mean to say with that? It's like we are not getting to the same position again in the same path, never, but we can come to the same position from different paths, of course, and in that case we only care about the longest. That's an interesting thing. Okay. Did I learn anything about this? I guess I have a better idea of how to form the like make an algorithm of my own, but not so much. And okay, let's get the sample input to what it was in the beginning. This is weird that we are getting the right answer for the sample, but not for the actual inputs, which is sad. Maybe we can print the paths and see if we can see something. I doubt that we will find anything useful in the actual input because it's quite big. But let's do it, I guess. We can avoid this print here. Let's longest path is gonna be the k shortest. Last, let's unwrap, and this is the path itself, so not the cost, the path. There should be a vector of usize, perfect. And your problem here is, borrow this thing. I want to print this and print it with color. I think we did something very similar to this for another maze thing. Oh, look at that. It was what was this? Clumsy crucible. Yeah, beautiful. We're gonna have something very similar to this. Let's copy and let's paste, and let's do something similar. We're gonna go for X and Y in the grid, and what we want to do is, I wanted to copy this code because I was interested in the color because I never remember how to print things with color. But okay, longest path, sure. What we want to do is see if the XY tile is part of the path, and then we just print it with a color. So that's it, that's what we want to do. So let's say, why is it doing so much things here? If the longest path contains the XY, then we are going to do something like this, right? Do we need the format? Do we need all of this stuff? I think we don't. Let's break this down into 3. We're just going to push first the color thingy up to here, then push the single tile character and then push the reset code for the color like this, right? Kind of contains, expects reference, a tile is sure, have that, and all of this is not needed anymore. And what about that? If we print this for the sample, oops, oh, we don't have an else condition, which we want. We want to do this on the else. You don't like that because for else doesn't exist. It is if else. And if we print this now, ooh, look at that. Look at that. It's always so nice to print things. Ah, this is beautiful. We see the path. Great. And this is the path, right? Yeah. Because this is the actual answer for the sample input. That's great. So let's actually do this kind of thing, but in the real terminal or bigger terminal, and let's run it in release mode because we know it's slow, and we'll run for the actual input. And it's gonna take some time because this is freaking slow. But will we see something? Well, we should see a path, actually. We know that we found one. We found many, actually. 252 to be precise. But I don't know what we will see. So we shall see. All right. Look at that. Look at that. Most of the maze is not being covered, which is interesting and suspicious too. So look at that. There is a bifurcation here, for example, that is not being taken, but presumably that should be because either that doesn't lead us to the output or it's not longer. But this kind of zigzagging things in here make me a bit suspicious of, because this thing is very dense, and like you can take, like it's weird that this doesn't look like the longest, although we know that it's not too far from the longest because we know that the answer is less than 2500, and this is 1950 or something like that. So that is interesting, but of course I cannot see anything here because like analyzing this would be maddening. But it is interesting to see like how we went over here. There aren't that many bifurcations, so there's another one here. Yeah, I find it curious that we are not taking these long detours. I mean, there are these are other paths with the which the algorithm should have analyzed already, and they are not the longest. So we know that, right? When we print everything, we know that these things are sorted. Oh wait, are they sorted? Look at that. There's a 1950 here. Wait, what? 2006? What? 2090? Wait a second, this is not... this is not sorted. This is wrong, right? Like, am I tripping? Like, this thing was supposed to give us the return paths include both the start and the end node and not ordered by their cost, starting with the lowest cost. This is not very right, I think, because it says like they are ordered by their cost, but clearly they are not. Some of the costs are longer. So I was just doing this wrong. Yeah, there are longer paths. So I had all the paths, but I just assumed that the last one was the longest. So do I have the answer already? Is this... Let's comment this because it's a very pretty thing. I probably want to have it. But this is not the longest path. The longest should be, well, the longest of this k shortest path. But I think this is a bug in the library, and like at least this sentence in the documentation should be changed, I think. Or the implementation should be changed to like sort these things. But yeah, okay. We have the k shortest paths. Let's get the maximum of this, right? How do we say this? Longest path is not the last. It should be the max, but do we have a max? Not like this. We can iterate over this and get a max. Well, we could get the costs and then get the maximum of those. So yeah, right, we can say path and cost and map to the cost and then get the maximum of this, and let's unwrap, not think about problems. Although if we want to print this, it's like yeah, let's get this and let's say longest path and longest path length. And just get, not do the mapping and say max by key is what I want, probably. What is the difference of max by and max by key? Yeah, this compares the two things. Yeah, no, I want max by key and just have a path and a cost and just give me back the cost. And we are just going to print. I leave the code for printing the path, the maze, because I think it's very pretty, but let's print line the cost, longest path length. Yeah, let's actually leave this thing because I don't know, because I want to see it again. Oh, because also I want to see how the longest path looks now that we are getting it. Because what we printed was the last of the paths, not the longest. And this is super slow, so I will have to change this to some like more ad hoc implementation of this thing. But we'll see that when we get... Oh, look at that. It's a very different path. Yep. And look at that. It's also quite larger. So is this the correct answer? Now I'm more confident of this. And it is. Okay. Very nice. And I don't know if I want to continue to part 2 now because, well, yeah, let's read it, but I will probably end the video, take a break before solving part 2. Also maybe think a little bit about a better approach for part 1, but let's see what part 2 is about. As you reach the trailhead, you realize that the ground isn't as slippery as you expected. You'll have no problem climbing up the steep slopes. Now treat all slopes as if they were a normal path. You still want to make sure you have the most scenic hike possible. So continue to ensure that you never step onto the same tile twice. What is the longest hike you can take? In the example above, this increases the longest hike to 164 steps, 154 steps. Okay, so now there are many more possibilities. Find the longest hike you can take through the surprisingly dry hiking trails listed on your map. How many steps long is the longest hike? So, okay, actually, we can solve, I think, part 2 by doing the same, like using the k shortest path thing again. So I want to, let's add all of this. This is not a very nice, like I didn't think I was going to do part 2 on this session because I'm a bit tired already, but it seems to be like a simpler problem to code, but I don't know if we'll get to see the solution. Like if it's going to run in proper time. So let's actually forget about, yeah, I've added this as part 1, so it's already stashed into Git. So let's do something for what would part 2 require? Basically, we don't do these checks, right? We only care about walls, but we don't care about this. We can climb over this, so let's remove this. And these, look at Clippy, it wants us to, yeah, look at that, if let tile, which is the same as asking if the tile is a wall. Sure, thanks Clippy. We do that. Oh, we were also doing this thing which we don't care about. We don't care about that. And I think that's all that we need to change for part 2. Let's run this for the sample now. $152, okay. And it found 12 paths instead of 6. Interesting multiple of 2. So let's do the same now, but with the actual input. And I don't know how long this will take, because this increases the amount of possible paths by a lot. And if it finds 1,000, it means that, well, we probably won't have the longest path. How much longer? Because this basically makes a lot of previously impossible paths now possible. So it's going to have, like, look at, for example, this bifurcation here is, you know, you're gonna have more paths to investigate at every crossing, basically. So it's probably going to take longer, but I don't expect it to be like exponentially longer, right? Maybe twice as long, 4 times as long, but not like 100 times longer, right? I never timed this thing. I probably should have. It's definitely not a acceptable solution, like for a fast advent of code solution. I would like to make this much faster, but well, we shall see. So yeah, this worked for the sample, but it's taking its sweet time for the input. And I'm worried that it might print that it found 1,000. If it says we found 1,000 paths, then it's not going to be the longest, or maybe it found the longest already, but we don't know. But yeah, it was also very interesting to find that this library didn't really gave us the solutions sorted. I will have to take note of that and report this back to the library. I think that is the correct thing to do. So let's take a note of that. To do report by on Jens algorithm. Not report, but report bag and Jens algorithm not returning paths sorted by cost. Something like that. And it's not really finishing in time, it seems. So it is taking much longer. It surprisingly though, it hasn't reached our K of 1,000, but it's so slow, and this isn't like that big, I think. But it's interesting. It's quite interesting, like the way that this thing behaves. I wonder if I can use this algorithm, Jan's algorithm, but reduce the connectivity of this graph to make it much smaller, and do the thing that I mentioned of because for example, right now it's going to have the graph that we are considering has so many nodes. Basically each dot is a node, and you can see that there aren't any bifurcations here at the start. There's one here. It's the first one, I think, on the whole thing. So we could say that this node connect to this node with the cost of walking all of this, and then keep going either to the right or down. But with a much shorter much not shorter, but yeah, much smaller graph of connected nodes. That should, I think, speed things up considerably for this algorithm, but I also think that this algorithm is not really great for what we are doing, because it's trying to find the K shortest path, and we don't care about the shortest path, we care about the longest. So it's like whenever we I'm not sure about, when we have found a path from beginning to end, and it goes through stuff, through nodes and whatever, and this bifurcation nodes. If we are considering another path and we get to a same bifurcation that we saw on the first path that we found, we can consider the cost there, and if it is a smaller cost, if we took a smaller path to get there, we can. But okay, if we start with the shortest path, then that won't happen. It's interesting. It's quite interesting. Oh, it did finish. And this is for sure not the right answer, right? because it's even shorter than before. That sucks. And it found 1,000 paths, but in those 1,000 paths, the longest, look at that, is a very winding path also, but the longest is no longer than the longest that we found previously. That sucks. So this basically increases the connectivity of our graph by quite a bit. But it's not so, it doesn't really work. I'm tempted to leave this thing running for a bigger K. Let's say, I don't know, K 100,000. So this will take very, very long, but maybe we'll get an answer for part 2. I mean, it should, I think. So yeah, I can grab something to eat and leave this thing running, I think, for K 100,000. Let's do that. Also, my cats, I don't know if you heard, but one of my cats was asking for food, I think. They are hungry. So yeah, I will leave this running now, and I will pause this video and maybe come back when I have an answer and see what happens. The shortcut is meta-w. So see you in a bit. Okay, and I'm back. And this is still running, and it's been more than an hour and it hasn't finished. So apparently, yes, it did take much longer than the part 1 solution. So I think I'm going to, well, end the video here and try to think about a better way of solving this. I probably leave this running because it's not taking. I had killed it before because I didn't run it with timing. Now I'm running it with a time command to see how long it takes. But yeah, it's not finishing anytime soon, it seems. And it's surprising, like the change for part 2 was apparently only like increasing the connectivity of things. And well, before we reached the 1,000 paths, but now we are running till 100,000. Oh, I don't know where I went. I can probably check this. Where are we? The yen thing. We have the K. So yeah, this is running for K from 0 to K 0 to K minus 1. And this is probably missing a sort by here to allow well, to fix the bug or inconsistent behavior that we found. But yeah, it's interesting. We can kind of take a look at this. It seems to be linear on K's, although, well, yeah, this is a linear axis. Previews. Okay. Yeah, this is not finishing in time for sure. So what should we do? I think we can get rid of the changes we did for part 2, commit the naive solution we have for part 1, and call it a day with that. So I'm going to discard these changes. Then, I mean, the part 1 solution does have some, well, this printing of the map and whatever, but it's fine. It's finding the solution that we want. the sample output, maybe we can, how many did we expect for the sample is 164, 154. Although, okay, let's leave it with only the part 1 answer, I guess. Longest path length, sure. We can, okay, shortest, blah, blah. Let's do something. Let's change this to an assertion. So anyhow, ensure, let's ensure that this is less than k, and if it's not, we'll say like found too many paths. Whatever, like we don't expect this. But if it's less than k, then we should have the maximum, and we get it here, and we can put this behind an if. So just like we were doing here, if we pass the debug environment variable, we do the thing, otherwise we don't. So let's just put an if here. If this is I guess we have to import this. Yep. So if this is okay, it is something, we'll put all of this printing inside of here, and then we print the longest path length. Sure. We have the sample output, the input, and the answer for part 1 was this. So let's copy this and put it on the answers file. So day 23, part 1 is this. Okay, and we can probably run check all, which will take some time to run. It was already taking like a second to run all the previous solutions, and this one took, well, quite a few seconds. I don't remember how many, but it should pass the check, I think. Yeah, let's leave that as part 1. So add the answers, add these changes that we had, the readme, just a to do. So let's commit this. Add day 23, part 1 solution. Let's say naive and slow part 1 solution. Okay. And well, the checks are taking way too long. This is not nice to have something take this long. So I have some ideas of how to improve this. The most obvious, like still using the same approach of using this Jens algorithm, but instead of going through all the grid and considering every tile a possible node on this algorithm, we can first like pre-process the grid and build up like an actual graph. And how would that look? It would, where's the sample? So in the graph, we could just have the nodes, like the starting node, the end node, and then only the bifurcations, like what is the first bifurcation? Like this node that bifurcates into 2, and then the connections between them with their cost. So from the start, one connection from the start would be this node with the cost of this length. And then this one will connect, for example, with I don't know, with this, for example, is another bifurcation with that cost, and so on. And the connectivity of that graph is not too high. Like a bifurcation would, like by definition, have 2 connected nodes, or maybe 3. Or well, there are some that have 4, but it's never more than 4, which corresponds to the 4 directions. And you always come from a previous one. So, you know, if it's 4, it doesn't matter, because, you know, you're not going to go back. The algorithm is not going to do that. But that will reduce the size of the graph by a lot, like considerably. And maybe that would be enough to have this very naive algorithm work. And then, well, the other idea would be to do that, but implement our own like longest path algorithm instead of just using, because this thing is meant to find shortest paths, and we're just finding lots of shortest paths and then you know, getting the maximum of those, which is not a great idea, I think. I don't know exactly how I would implement this, but it would be something kind of like kind of a brute force solution, but it depends on how many branches we have. Apparently, like for the part 2, the branching is enormous because, well, it is quite high. Either that or this algorithm is very slow, or a combination of both. I suspect the latter, but we don't know. Probably the checks have passed. Yeah, okay, the checks do pass. That's cool. The answers file is fine. Okay, everything looks quite alright. Oh, I have already committed this, so that's fine. We can maybe do a little thumbnail for this, although, I mean, this looks like a nice thumbnail, right? Look at that giant maze. We can maybe make the font size smaller to see it all, although it is, well, it is already quite long. Quite big, I mean. But yeah, look at that. That could be an acceptable thumbnail, and although I would like to sort of say what this is about, although that's not readable at all. Yeah, I wanted to say something like have a thumbnail that says like anti-Dijkstra or something like that. Like that is what we're doing here. But I mean, this looks quite alright. And I mean, thumbnails, are they important? I don't know. YouTube says yes, but who knows? Anyway, I don't know if I will do another session for this today because it's already late and I think I'm not so sharp anymore. But I will definitely try to improve this this solution. Even I will leave this running because it's just, you know, it doesn't harm anyone except my computer, but it's only using 1 core, so it's fine. But yeah, we have to definitely revisit this bad solution, but that will be for another day, I think. So, all right, that's the end of this video. As usual, if you have been, thanks for watching and see you later. Bye bye.